If you like the content of this video, please do press the like button and subscribe. A differential equation is an equation involving an unknown function and its derivatives. It is called an ordinary differential equation, often abbreviated as ODE, if the unknown function depends on only one variable. If the unknown function depends on two or more independent variables, the differential equation is called a partial differential equation. A differential equation, along with subsidiary conditions on the unknown function and its derivatives, all given at the same value of the independent variable, constitutes an initial value problem. The subsidiary conditions are initial conditions. If the subsidiary conditions are given at more than one value of the independent variable, the problem is a boundary value problem, and the conditions are boundary conditions. A solution to an initial value or boundary value problem is an equation and satisfies all given subsidiary conditions. The standard form for a first-order differential equation in the unknown function y of x is shown now, and the differential form is shown next. Next, let's understand the definition of order and degree of a differential equation. The order of a differential equation is the order of the highest derivative in the differential equation. A first-order differential equation is represented in terms of the functions p of x and q of x. The degree of a differential equation is represented by the power of the highest order derivative in the differential equation. Note that in the last equation, the degree is not defined. Let's now investigate methods for solving ordinary differential equations. In the first method, we separate the variables to reduce it to an integrable form. Thereafter, it is simply a process of integrating to get to the solution of the ordinary differential equation. In method 2, we reduce the ordinary differential equation to a separable form, where dy of dx is expressed as a function of y by x. If we let y as ux and apply the chain rule, we arrive at equation 4, which is separable, and which we can integrate to get to the solution. In method 3, we consider the situation where an ODE has an implicit solution. For the implicit solution to exist, the conditions involving the partial derivatives must be satisfied, and if that is the case, the solution is straightforward. Here is an example. We now consider an ODE, which is inexact. This is because the conditions involving the partial derivatives is not satisfied, so we cannot apply the previous technique. If we try to do that, we will run into a contradictory solution. Sometimes, it may be possible to make the equation exact by multiplying it by a factor f, which is a function of x and y, and impose a condition to make it exact. Then, we simplify f by making it depend only on x. We can solve for f of x as well as f of y. These functions are called the integrating factors. In this example, we compute both the integrating factors The first integrating factor, r, is a function of both x and y, and so it is not possible to perform the integration. The second integrating factor, r star, is a function of y only, and we can integrate. We multiply the equation with this integrating factor, identify m and n, and verify that the conditions on the partial derivatives are satisfied. We can then solve the partial differential equation involving m and n, and evaluate the integration constant to get to the solution. In method 4, we focus on solving first order ODE. We first solve for the homogeneous equation, that is, when r of x is 0. Using separation of variables from method 1, we can easily arrive at the solution for the homogeneous equation. We now find the particular solution for the non-homogeneous part. Let's multiply the ODE by f, which is a function of x only. Then, we make a clever choice by using a condition, as shown in the box, in equation 8. This simplifies the ODE, and we will use this form later. Based on the condition we have set, we find f in equation 10. Now we substitute f in equation 8, and solve for the particular solution corresponding to the function r of x. The complete solution to the first order ODE is the sum of the solution to the homogeneous equation plus the particular solution. We now consider an important ODE known as the Bernoulli equation. The Bernoulli equation is a nonlinear ODE because of the term y to the power n. But if we substitute with u as y to the power 1 minus n, we will see that the ODE takes a linear form. We compute u prime in terms of y prime. Then, we substitute the value of y prime from the original ODE, which we can solve using the solution in method 4. This brings us to the end of the session on solving first order ordinary differential equations. In the next session, we will look at second order ordinary differential equations.